Hello, welcome to another video. Today we're gonna pit these two topics against each other. Since I'm biased, you already know which one's gonna win. Here are some videos about finite cyclic groups and two's complement. If you want me to make my own crash courses about them, let me know in the comments below. A finite cyclic group is a group that is finite. A cyclic group is a group that is generated by one element. A group is a set together with an associative algebraic structure that contains an identity element and an inverse for each of its elements. There's more to groups than what can fit in a continuous 10-year-long video. Here are some examples. The set of integers form a group under the addition and is an example of an infinite cyclic group. Sn is the symmetric group of n letters. For example, S3 is the set of all the different ways to rearrange three things. It's an example of a finite group. A3 is the alternating subgroup of the symmetric group of three letters. It's an example of a finite cyclic group. Here are more examples. The element of S5 that has the arrangement 5, 1, 2, 3, 4 generates a cyclic group of 5 elements. The XOR truth table also forms a group. The set is the set containing 0 and 1, and the group operation is the XOR operation. Here are some facts about cyclic groups. There is only one infinite cyclic group up to isomorphism. That is, any infinite cyclic group is isomorphic to the group of integers. For each natural number n, there exists only one cyclic group of size n, up to isomorphism. Here are the definitions of isomorphism and isomorphic. In a nutshell, an isomorphism renames the group elements but preserves the group structure. Two's complement is a way for computers to represent some negative integers with binary numbers. Here is a table. In using two's complement, we sacrifice 8 to 15 so we can use these combinations for negative numbers. But for 8 digits, we sacrifice 128 to 255 and use negative numbers like the one on the right. And it works well, particularly when using the pre-common core method of addition. For example, 7 is 0, 1, 1, 1. In binary, negative 5 is 1, 0, 1, 1 in 2's complement. If we add them up, we get 1, 0, 0, 1, 0, but we have to drop the last carry to fit in the 4 digits. The result is 0010, and that represents decimal number 2, which is what we expect when we add 7 and negative 5. It also works in other combinations, negative plus negative and negative plus positive. How do we get the negative number without looking at the table? We invert the bits, then add 1. For example, 0100 is 4 To get -4, we invert the bits, becomes 1, 0, 1, 1, then add 1. It becomes 1, 1, 0, 0. This is -4, or the 2's complement of 0, 1, 0, 0. That's pretty much 2's complement. The method depends on the number of binary digits. We review how to construct a finite cyclic group of order 16. We need 16 elements: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. That's it, 16 elements. 0 is the identity element and 1 is a generator. 2 is 1 plus 1. 3 is 2 plus 1. And so on. The plus is the group operation. When it comes to 15 plus 1, it has to be within the set. We make 15 plus 1 equal to 0. Anything else would make this group have fewer than 16 elements. Remember inverses? Each element in the set has an inverse so that when we plus them together, we get 0. 0 plus 0 equals 0, so 0 is the inverse of itself. 15 plus 1 equals 0, so 15 is the inverse of 1. We can't just put minus in front of 1. It has to be within the set. 14 plus 2 equals 0, so 14 is the inverse of 2. 13 plus 3 equals 0, so 13 is the inverse of 3. And so on and so forth. Let's rename these. 0 becomes 0, 0, 0, 0. 1 becomes 0, 0, 0, 1. 2 becomes 0, 0, 1, 0 until we get to 15, which becomes 1, 1, 1, 1. If we use the inverses, they look like this. Let's put some back. Now look at this. Aren't they the same thing? The numbers were just renamed. Everything else works the same. 2's complement is an instance or an application of finite cyclic groups. What's crazy about 2's complement is that we have to make a distinction between positive and negative numbers. In finite cyclic groups, there is no positive numbers. There is no negative numbers. No overflows too. And they say I'm a dreamer, but I'm not the only one. In signed integers, the computer science people decided that the leading binary digit determines the sign, so that the binary numbers that start with 1 is negative and the rest are non-negative. We use the tilde notation for bitwise not in C. I mean, it is in C. In C, tilde is the bitwise not. Here is the truth table for the NOT gate. If a binary number has all ones in its digits, it can mean two things. It is the bitwise NOT of a binary number with all zeros in its digits, and at the same time, it represents -1 in finite cyclic groups. Here, tilde x is the bitwise NOT of x, and -x is the natural inverse of x. So, tilde 0 equals -1. Looking at the XOR truth table, the XOR operation becomes a NOT operation if one of the inputs is 1. So 1 XOR A is not A. Do this to all digits, we have 1, 1, 1, 1, 1, 1, 1, 1. Bitwise XOR a binary number results to bitwise NOT of that number. Also notice that XORing with 1 is also subtraction from 1. If we all have 1s in the minuend, bitwise XOR is a pre-common core subtraction with no borrowing happening. So subtraction from -1 is exactly bitwise NOT. But in finite cyclic groups, there is no subtraction. There is only adding an inverse. Now we have an equation where we can solve for -x or the natural inverse of x. We can add 1 to both sides as we would in preschool algebra, and since cyclic groups are commutative, we can rearrange the left-hand side to -x plus -1 plus 1, that is equal to -x plus 0 or -x. The right-hand side is tilde x plus 1, which is taking the 1's complement, then adding 1. So this method gives the natural inverse in finite cyclic groups that can be represented by binary numbers with a fixed number of digits. Cyclic groups can be extended into a commutative ring with unity. That is also why multiplication sometimes works with 2's complement. That's it. Thanks again for watching. See you sometime later. Bye.